Welcome to Creative World. In this video, I will show you the simulation of automatic power factor correction system developed in Proteus software. This video will include only the information related to components used in simulation and the simulation results. I will make a separate video for programming which is used to program Arduino inside this simulation. For now, we will just focus on the components and the output results retrieved from this simulation. We have different loads that are connected across an AC source through this rotary switch. In order to shift load, we have to swap the positions of this rotary switch. At a time, only one source will be connected across this voltage source. This voltage source is acting as a utility connection because it is rated on 220 volt and 50 Hz. Now, if we focus on these loads, this first load is pure resistive load having the value of 45 ohm. Second load have the value of 29 ohm, while it also have some inductance connected in series connection to this load. The value of inductance is 111 millihenry. Similarly, this load have the value of resistance 24 ohm and the value of inductance that is connected in series with this resistance is 122.91 millihenry. Next one, the value of resistance is 19 ohm and the value of inductance is 131.86 millihenry. Similarly, next two resistances are connected to respective inductances in series with them. Now, if we focus from right side to left side, the value of resistance is decreasing but the value of inductance is increasing. So, it shows that whenever this branch will be connected across this voltage source, the power factor of this voltage source should be unity because there is no inductance inside this branch. But whenever this branch is connected across this voltage source, the power factor should be low as compared to other branches because the higher value of inductance exists inside this branch. So, with the help of this rotary switch, we will shift the loads across this voltage source and will observe different power factor values. Now, there is a voltage divider circuit that is connected across this voltage source in order to measure voltage across this source. This point PT will be considered as voltage point. Voltage across this 99 kilo ohm resistance will be fed to this Arduino on pin A1. Similarly, inside this simulation, we have two zero cross detectors. This zero cross detector is responsible for the detection of zero crossing of voltage, while this zero cross detector is responsible for the detection of zero crossing of current. Whenever both current and voltage will be in phase, at that time the output of this XOR gate will be 0. But whenever there will be a difference between voltage and current angle, at that time the output of XR will be high. Now, if we focus on other components of the simulation, this is an LCD to display all output results. An Arduino as a microcontroller is used inside this simulation to calculate the power factor and other values and display those values through this LCD. This Arduino is also responsible for the switching of different capacitors inside the system. Now, if we focus on the left side of the simulation, we have some relays that are connected to specific values of capacitors. This relay is being controlled through a transistor and this transistor is being controlled from Arduino output. So, first of all, the Arduino will calculate the power factor of the system. If the power factor of the system is down, so it will initiate the command to different transistors to switch relays on and add capacitors to the system. These capacitors will be actually added across AC voltage source. So in normal state, whenever the relay will be off, there will be no capacitor added to the actual network, because at this time the capacitor will be connected to normally open contact of the relay. But whenever this relay will be activated through the output signal of Arduino, this capacitor will be added across the AC voltage source to improve its power factor. Here the values of capacitors are different from each other, and those are increasing in steps. So if the value of power factor is decreased to very low level, in that case all of these capacitors will be added into the system. But if the value of power factor is close to the nominal value, in that case only few capacitors will be added into the system. So the addition of capacitors is totally dependent upon the value of power factor of the system. If power factor is too much low, all of these capacitors will be added. But if the power factor is not too much low, in that case a few capacitors will be added into the system. Now we will run the simulation and see the results. So let's run the simulation and see the results. First of all, only resistive load will be added into the system. So right now only 45 ohm load resistor is connected across voltage source. In this case the power factor should be unity, because we have only resistive load in the system. So you may see here the power factor is close to unity, 0.9. Okay, and the last message you may see that capacitors are out. It means no capacitor is connected in the system right now because the power factor is unity. You may also see here all of the relays are off and no capacitor is added into the system. Now we will shift the load. Right now we have added second branch of the load into the system. So due to the presence of inductor, our power factor will be decreased. You may see here the power factor is decreased up to 0.6 and capacitors are added into the system. After the additions of capacitors, the updated power factor is 0.8. So power factor is improved from 0.6 to 0.8. And you may see here 10 microfarad capacitor is added into the system. Because the power factor was very close to unity, so only one capacitor is added into the system. Now switch to the next load. In this case, the value of inductance is increased in the system. Due to the increase of inductance, the power factor value of the system will be decreased from 0.6 to 0.5. And after this, some other capacitors will be added into system to stabilize the power factor. You may see the updated power factor is 0.75 as compared to previous power factor which was 0.5 due to the load. And you may also see here, in this case, two capacitors are added into the system to stabilize the power factor. Now switch to the next load. Further value of inductance is increased. So due to the increase of this inductance value, the power factor will further decrease. You may see in the screen the power factor is further decreased to 0.4, and due to the decrease of power factor, further capacitors are added into the system. Right now the updated power factor is 0.79. Switch to the next load. In this case, the power factor of system will further decrease to 0.3. And after the addition of capacitors, the power factor is 0.89. And you may see here, right now 4 capacitors are added into the system. Switch to the next load. At this time, the power factor of system is severely decreased to 0.2. So you may see here, at this stage, all of these capacitors are added into the system to inject reactive power into the system to compensate the power factor reduction. And after this, you may see that the updated power factor is 0.85. We will also confirm the ejection of capacitors from the system by shifting load to resistive network. At this stage, because of pure resistive network, the power factor of system itself is 0.9 and because of this power factor, all of these capacitors should be out from the network, and you may see the results. All of these capacitors are out from the network. So this was all about the implementation of automatic power factor correction system in Proteus software. Thank you. See you again in next video.